Good morning, everyone. Today we'll be discussing further tests for frequency tables. The major thing that we'll be discussing is chi-square test for independence of attributes. We have already seen chi-square test for goodness of fit. Independence of attributes is another important study where chi-square tests are used. So what do I mean by independence of attributes? Suppose I have two categorical variables, say x and y, and I want to see if there is any association between these two variables. So association of what sort? So generally we want to see whether say one is a cause for other, or whether value of x, particular value of x, does it increase the likelihood of some particular value of y. So typical example that is given in this study is x is a smoking status, whether a person smokes or not, and y say whether a person gets lung cancer or not. Okay, so there are two categories, yes, no, for both these variables, and we want to see whether being a smoker, does it increase the chances of lung cancer. So such type of studies can be done via chi-square test for independence of attributes. So the null hypothesis is the two attributes are not related, so there is no association between the two attributes. So between the two variables under study. So here it would mean that whether you smoke or not has no effect on lung cancer, with no effect on probability of you getting lung cancer. That would be null hypothesis. Alternative hypothesis is there is an association. Okay, so there is an association between the two variables. So whether you smoke or not does change the probability of you being getting lung cancer. Okay. So what type of data is collected? The data is again a frequency distribution. Okay. So suppose I have x here, yes, no, and y here, yes, no. So we have collected data on some people. We have asked them two questions, whether they have lung cancer or not, and whether they smoke or not. And the total number of people is whatever is total number of people, let's say 1000. We divide it into these 4 cells. Okay, so suppose we have say 180 people who smoke and who have lung cancer. Okay, so x is smoking here, smoking status. Then suppose we have say 100 people who smoke but don't have lung cancer. Then we have say 20 people who don't smoke but have lung cancer, and we have remaining 700 people who neither smoke nor do they have lung cancer, suppose. Okay, so this is just from the data collected. For every person we can record whether the person smokes or not and whether the person has lung cancer or not. So we can classify people into 4 types and a count is given here. Now using these counts we need to decide whether there is an association between smoking and lung cancer. Means whether being a smoker, does it really increase the chances of getting lung cancer. Okay, so let us see. Now we have we will compute totals. So here I have 200 as column total, 800, here I have 280 and 720. Okay, now if smoking and lung cancer were not related at all, then it would mean that probability of having yes here as well as yes here, these two are independent of each other. And we know from basics of probability theory that probability of A intersection B is probability of A into probability of B if A and B are independent. You must have done this in the first semester. Okay, so that is the logic behind the construction of test statistic here. So we first compute what is known as expected frequencies, like we did in goodness of fit. So expected frequencies under H naught. Under H naught means if the null hypothesis is true, then what are the expected frequencies? These are observed frequencies. So this is O1, this is say O2, O3, O4. So these are observed frequencies and we'll compute expected frequencies. So if smoking and lung cancer are not related at all, if smoking does not change the probability of getting lung cancer, then probability of each cell can be obtained by probability of by the product of marginal probabilities of row and column. So probability of smoking equal to yes and cancer equal to yes would be probability of smoking equal to yes into probability of cancer equal to yes if H naught is true. Okay. So under H naught. Now what does it mean? Probability of smoking equal to yes is out of total data that we have, how many are smokers. So we have 1000, out of which smoking equal to yes is 280. So probability of smoking equal to yes would be 280 divided by 1000. Okay. And probability of cancer equal to yes would be this 200 divided by 1000. Okay. These numbers are actually misleading. We don't have 20% cancer occurrence, but I have taken just arbitrary numbers. Okay. So this is probability, and from probability, how do I compute expected frequency? Expected frequency for that cell would be total number of people, that is 1000 into the expected probability. Expected probability. So this is 1000 into 280 by 1000 into 200 by 1000. So this gets cancelled. This is 5 and I'll have 5, 5, 56, right? So expected frequency here is 56. Similarly, I have to compute for other cells what are the expected frequencies. So for this cell, it would be this total into this total divided by 1000 two times into 1000 one time. So basically we are taking 1000 only once. So 280 into 800 divided by 1000. So the general formula is column total of that column, row total of that column divided by total number. So 1, 2, 3 gets cancelled, 1, 2, 3. So I am left with 204. Okay. So we have 204 as expected frequency here. Then for this we will have 200 into 280 divided by 1000. So this is 56 here, and the last column would be 800 is the total into 720 is the row total divided by 1000. So that is 576. Okay. So these are 4 expected frequencies. Now the chi-square test statistic looks exactly similar to the earlier chi-square test statistic, that is sum over OI minus EI whole square divided by EI, I going from 1 to, here I have 4 cells, so 4. So let us compute that. So OI observed is 180 minus 56 in the first case. So 180 minus 56 whole square divided by 56 plus 100 minus 204 in the next cell. So 100 minus 204 whole square divided by 204 plus 20 minus 56. So 20 minus 56 whole square divided by 56 plus 700 minus 576. So 700 minus 576 whole square divided by 576. Okay. So we have to compute each of these values. So let me try and compute these values. So 180 minus 56 whole square divided by 56. So the first term becomes 274.57 plus 100 minus 204 whole square divided by 204. So the second term becomes 53.02 plus 20 minus 56 whole square divided by 56. So that is 23.14 plus 700 minus 576 whole square divided by 576. So this is 26.7 roughly. Okay, 70. So if we add these, we have 274.57 plus 53.02 plus 23.14 plus 26.7. So the total turns out to be 377.43. Okay. Now we have to compare this with the tabulated value of the chi-square test statistic and decide whether this is large enough to reject H0. Okay. So under the null hypothesis, distribution of this test statistic, that is OI minus EI whole square upon EI, under null hypothesis it is chi-square into R minus 1 C minus 1, where R is number of rows and C is number of columns. So here my number of rows is 2, number of columns is 2. So I have to compare with chi-square 1. So let me go to the table, chi-square tables, and see here for chi-square 0.95 we have to check, because if we want at 5% level of significance. So with chi-square 0.95 you can see here with degrees of freedom 1 the value is only 3.841. So the value is very small. Okay, 3.841. And what we are getting is very large value. Okay. So we are very strongly rejecting the null hypothesis. Okay. The value is supposed to be 3 point something and we are getting 377 point something. So we are rejecting null hypothesis very strongly. So we are saying that okay, smoking and lung cancer are associated with each other. Okay. Now we can just go back and see the individual values that would tell us the picture association is in which direction. Okay. So let me go back. Okay. So see here, expected frequency is 56 and observed frequency is 180. So expected frequency is much smaller. So observed frequency is much larger than what is expected. So it kind of tells you that yes, probably smoking is causing lung cancer, because with smokers the expected number of lung cancer patient is much higher than what it should be, and on the other hand difference is also high but in the opposite direction. So the expected difference of expected count of healthy people who don't smoke is less, 576, but the observed count is much high. So many more people are healthier than expected if there was no association. Okay. Similarly here also the association is in the the relationship is in the opposite direction. Okay. So this kind of tells you that yes, smoking and lung cancer are possibly related. Smoking is probably the cause of lung cancer. Okay. To fully quantify this, there are two other terms that can be used. So there is something called as relative risk. Okay. And there is another thing called as odds ratio. Generally, there are two types of studies. One is known as prospective study and other is known as retrospective study. So what we do in prospective study is, suppose in this smoking lung cancer example, if I want to carry out a prospective study, what I'll do is, I'll first take a sample of some smokers and some sample of non-smokers. I will keep observing these people for a certain duration, let us say 20 years. And in 20 years, we will see how many smokers developed lung cancer and how many smokers did not develop lung cancer. Similarly, in non-smokers, we would record how many smokers developed lung cancer and how many did not develop lung cancer. Okay, so here these numbers, total number of smokers and total number of non-smokers, are kind of fixed in the beginning, whereas the number of people who develop disease and number of people who do not develop disease is random. Okay. In the retrospective study, opposite is true. In retrospective study, I first take a sample of patients and sample of healthy people, and then I go back and see out of these patients how many were smokers and how many did not smoke. Similarly, in healthy people, we would record how many were smokers in the past before they developed the disease and how many did not smoke. So here, number of patients and healthy people is kind of fixed and number of people who are smokers or non-smokers is kind of varying. Okay, so it is important whether you are doing a retrospective study or prospective study, you should know that. So in prospective study, generally one uses relative risk, and in retrospective study, odds ratio. So what is relative risk? Relative risk kind of quantifies what are the chances of, developing a disease if you are a smoker. Means if you have a risk factor, how does your probability of developing that particular disease increase? So relative risk is computed from this table again. Okay, so this is the status of risk factor being present and this is the status of disease, yes, no. So if I call this as A, B, C and D, then relative risk would be defined as A upon A plus B, so A plus B is here, to C upon C plus D. C plus D is this total, right? So relative risk is defined as A upon A plus B to C upon C plus D. A upon A plus B is probability of people having developed a disease when they were when they had risk factor. So probability of having developed the disease in a group where risk factor was present. So in a group with risk factor divided by C upon C plus D is probability of having developed the disease in a group with no risk factor. So we kind of tell how many times the chances are more if you have the risk factor. Okay, if you have the risk factor, then you have more chances or less chances, and if more, how many times more. So here 180 upon 280 and 20 by 720. So 180 upon 280 and 20 by 720. So I'll have 18 upon 28 into 72 upon 20, right? 22. Am I correct? So this would become 18 upon 28 into 36. So 162 divided by 7. So this is roughly 23 point something. Okay, as I said, my numbers are arbitrary, so these values are huge. In reality, they may not be that big. Okay, so we are kind of saying that smokers have almost 23 times more probability or more chances of developing the lung cancer than non-smokers. Okay. However, if your study is prospective, then if your study is retrospective, then relative risk has less importance because you are not deciding the number of people who have risk factor or not. You are first deciding the number of patients and number of healthy people that you want to study, and then going back and then checking. So in such cases, you focus on what is known as odds ratio. You might have heard the word odds in terms of gambling or betting. So odds are probability of, success to probability of failure kind of thing. Okay. So here in the same table, I have A, B, C, D here. So risk factor yes, no, and disease yes, no. So generally disease yes, no we call as cases and controls in retrospective study, just to indicate that this has what got them in the study. Whether they are a case of disease or whether they are from the control group, that is with no disease, that would matter in deciding whether they enter the study or not. Okay. So these are the totals. So now we see that, so if you have a risk factor, then the probability of you being a case, that is you having a disease, was A upon A plus B, and in the control, probability of being a control was B upon A plus B. So odds of being a case in people with risk factor, in people with risk factor are A upon A plus B upon B upon A plus B, right? Because odds are always probability of success to probability of failure. So probability of success here is probability of being a case. Okay. Similarly, odds of being a case in people with no risk factor. So odds of being a case in a group with no risk factor is C upon C plus D divided by D upon C plus D. And then odds ratio is ratio of all these. So this A plus B gets cancelled, C plus D gets cancelled. So it is A by B into D by C. Okay, basically it is A by B upon C by D. So this becomes AD by BC. Okay, so in our case it would be A into D. So A into D means 180 into 700 divided by 20 into 100. Okay, so 180 into 700 divided by 20 into 100. So it is 9. Okay, so odds are 9 times. So in relative risk as well as in odds ratio, values greater than 1 indicate positive association, that is having that particular risk factor increases the chances of disease. Values less than 1 indicate negative association, that is having that risk factor decreases the chances of getting the disease, and value equal to 1 indicates no association. So whether you have the risk factor or not does not alter your probability of getting the disease. Okay. Of course, statisticians generally don't decide purely on the basis of these values. They give confidence intervals, but we won't go into that. Softwares can give you confidence intervals for odds ratio as well as relative risk. And generally, so if you have 1 here, so if confidence interval is here, that is completely to the right of 1, you conclude that yes, the probability of getting the disease is getting strongly increased with the presence of risk factor. If it is completely to the left of 1, you say it is getting significantly decreased by presence of risk factor. Okay, so this is about other two measures from frequency table. So this is all we wanted to study about frequency distribution and then measures associated with it. In the next lecture we would start regression. Thank you.